In this lecture or in this flip class video, we're going to introduce the divergence theorem, the last major theorem in this multivariable calculus sequence. So let's go ahead and recall what we've done that's similar to this so far, because this is going to be another theorem that fits in the same vein as the fundamental theorems we've seen so far. So we recall from the fundamental theorem of calculus from Calc 1 that if we integrate a derivative over an interval, that all that matters is what happens with that function on the edges of the interval, or the boundary of the interval. So that we've seen before, and we talked about this before. Similarly, if we do the fundamental theorem of line integrals, and we integrate the derivative, or in this case, the gradient of the function, which we're thinking of as a derivative, over some curve, all that matters is what's happening to the function at the edge points of the curve, or the boundary points. So we saw both of these when we were introducing Stokes theorem. So let's recall Stokes theorem as well. So in this case, we had S being a bounded surface with a boundary curve C, and we assumed that the orientations of S and C agreed. Then we considered a vector field so that the components of the vector field, P, Q, and R, they all have continuous partial derivatives in some region containing S. So think of, like, you have a surface, think of making a little like fat surface around it, and the partial derivative should be continuous in that region that's the fat surface. Then if we had those conditions, what Stokes theorem told us was that if we, in this case, we take the curl of the vector field, and if we integrate the curl of the vector field, so think of this as a type of derivative, so if we integrate the derivative over the entire surface, all that matters is what's happening to the function on the boundary of the surface. So not just plugging in points anymore, we are looking at just how the values of the function on the boundary of the surface. That can tell us everything about what's happening on the entire surface. So just like the previous two that we talked about, this is another one where you integrate a derivative, and all that matters is what's happening on the boundary. So that's what the divergence theorem is going to be about. So yeah, just to remind us that this was telling us it was a closed curve. But the divergence theorem is going to be the same type of thing. It's just going to move us up into 3 space. So now we're going to want a solid region in 3 space, which makes sense. We've been developing triple integrals in different coordinate systems. And our boundary is going to be the surface over that region. So you can think of like having a solid ball, and then the sphere, that would be our region, and then the sphere that's the edge of the ball would be our surface. And what we're going to see is basically follows the exact same pattern as the 3 theorems we just talked about. In reality, all of these theorems are special cases of what's called Stokes theorem when you're in a more general context. We just called them different names in calculus class, but if you were in a higher level math class, these would all just be Stokes theorems in just different cases. So in order to do the divergence theorem, we need to introduce a new type of derivative. We had the gradient, we had the curl. So now we're going to introduce what's called the divergence. So let's take our vector field here, F, with components P, Q, and R. And the divergence is much easier to calculate than the curl was. It takes much less time, because all we're going to do is we basically think of, remember how we thought of the curl as kind of taking the cross product. In this case, we can think of this as taking the dot product, only instead of multiplying, you're taking the delta x, delta y, the partial with respect to x, partial with respect to y, and partial with respect to z, and kind of dotting it with the f here. So it's partial derivative applied to p plus partial derivative applied to q plus partial derivative applied to r. So very easy to actually calculate the divergence of a vector field. And we saw that the curl was measuring the rotation of a vector field. The divergence is going to be measuring how that vector field spreads out. So let's go through and look at our examples, some of our examples we looked at before. So this was one of our early vector fields. So we're just taking xi plus yj, and this one we saw was spreading out in every direction. So this one we calculated had 0 curl because it wasn't rotating at all, but it's certainly spreading out. So we would expect a positive divergence here. And we see if we take the partial derivative with respect to x, we get 1. partial derivative with y with respect to y, we get 1. So 1 plus 1 is 2. So our divergence here is 2, which makes sense. It is spreading out. Now this was our rotational vector field. In this one, we had a positive curl for, so this the curl of this was just k, I believe, or some multiple of k at least. But we can see this one's just spinning in circles, so it's not spreading out at all. And if we calculate the divergence here, the partial of negative y with respect to x is 0, and the partial of x with respect to y is 0, so our divergence is 0, which makes sense. It's not spreading out in any direction, it's just rotating around. So now this is a little bit more complicated vector field. So you have cosine xi plus sine yj. So if we take the divergence, if we look at this, we can see it's spreading out in some places, but it's also contracting in some places. So like from here, it's spreading away, but from here, it's all being sucked in. So if we calculate the partial of this, of cosine of x with respect to x is minus sine, partial of sine with respect to y is cosine of y. So our divergence isn't a scalar, or isn't just a fixed number, not a constant here. It varies with x and y. So we get minus sine x plus cosine y. So that's what we can see when these two are equal. So like if x and y are pi over 4, then this is negative square root of 2, this is square root of 2. So we can see these are getting us some of our points here where we're getting zeros and then spreading out at other points. So this one depends upon where we're at in the plane, what our divergence is. So we can also obviously do this in 3 dimensions. So in this case, we saw this one did have a curl because it was rotating around, but it's not rotating around and staying in place. It's rotating around and going up or going down. So if I take the divergence of this, I get a 0 component from here, 0 component from here, but I get a 1 from this direction. So this is telling me I am spreading, this vector field is actually spreading out. It's rotating around and spreading out. So now that we know what the divergence of a vector field is, we can introduce the divergence theorem. So we're going to let V be some subspace of R, subset of R3. So think of some solid region like we've been looking at when doing triple integrals. It's going to be bounded, and it's going to have a smooth boundary surface. We're going to orient the boundary surface so that all the unit vectors point outward from V. So there's always this choice back in Stokes Theorem which way we wanted our vectors to point, or normal vectors to point when we had a surface. In this case, we're always going to have them point outward since it's a closed surface. If they point inward, you just put a negative sign in to orient them outward. So again, if I have my vector field where the components have continuous partial derivatives in some neighborhood of V, so think of just making your region in 3 space a little bit fatter, and then it has to have continuous partial derivatives all over there, then if I integrate the derivative, so the divergence, here's what we're thinking of as the derivative. And as I've said before, all of these things I'm saying are like derivatives, are actually derivatives. If you watch the videos online of mine on differentials, you'll see how these actually all come out as certain derivatives. But if I integrate this derivative over the entire region, all that matters is what's happening to the function on the boundary. So it fits exactly into the same setup as we had before for our fundamental theorem of calculus, fundamental theorem of line integrals, and Stokes theorem. All special cases of the same thing. Okay, and so some of these conditions are important. When we will see some examples in class and some that show up in physics where, like if we're using the gravity vector field here and our region contains the origin, then we don't have that these have continuous partial derivatives in that neighborhood. So we have to be careful. We can't just apply the divergence theorem directly. We'll have to use some tricks to be able to do it. So let's close with just a picture of a solid surface here. So think of like we have a donut here, solid donut, and then the edge of the donut, maybe the frosting or whatever, the glaze is our surface, and our unit normal should all be pointing outwards like this. So that's what it means in terms of that context.